As you continue to work with simplifying expressions, you'll find that exponents end up taking a pretty big role in a lot of the expressions. And we'd like to find some ways to work with them and become a little bit more comfortable with them. Let's take a look at several examples here of different problems and how we can simplify these expressions. In problem number 11 here, notice that we have a 3 times an x, and we want to multiply that by 5x squared. We did this a little bit with the distributive property anyway, but remember x squared means x times x. So if I was looking at this big multiplication, notice I could multiply the 3 and the 5 to get 15, and when I multiplied this x times x times x, I'd get x to the 3rd power, and that works really awesome. In this question right below here, notice we have 2x that's being taken to the 2nd power. Because what's in front of the 2nd power is that parentheses, that means it's going to be 2x times 2x. So if I multiply that together, notice that I get 2 times 2 is 4, and x times x gives me an x squared. Now, up here, if we follow this, notice that we have 4x, but it's being multiplied by 2x squared to the 3rd power. If we're following order of operations, we need to start out here with this outsidemost thing here, because this 3rd power has to happen to this whole set of things inside the parentheses. So let's look at what that would look like. Here I have 4x on the outside, then I'm going to need to multiply it by 2x squared times 2x squared. All right, well that's pretty fancy. So let's take a look and break this down a little bit farther. I've got 4x times 2 times x times 2 times x times x times 2 times x times x. So if I go through and multiply these together, I have a 4 times 2 times 2 times 2, which gives me 4 times 2 is 8, times 2 is 16, times 2 is 32. And then x times 1, 2, 3, 4, 5, lost count, 6, 7. There should be 7 altogether there. So we end up with 32x to the 7th as a resulting solution there. But it's because that 2x squared had to get written 3 times. We ended up with 4 times 2 times 2 times 2, and then the x from here, and then 2 x's from each of those repeated values there. Now, something to kind of keep in mind here, notice in this particular problem we have 2 plus x being taken to the 2nd power. So what's in front of the parentheses is the 2 plus x. So we can write that as 2 plus x times 2 plus x. In this particular case, that plus in there means we're multiplying binomials. And so the plus, anytime you see a plus in math, we're always like, no, because the rules get a little bit trickier. Rules with adding fractions are harder, rules with adding integers are harder, and rules when there's pluses and minuses in multiplying, that makes them harder too. So you have to remember to use FOIL. So here we do the 2 times 2 gives me 4 plus 2x. Then on the inside here we do x times 2 to get another 2x, and x times x to get an x squared. And I end up with 4 plus 4x plus x squared when I combine those like terms in the middle. Okay, so do be aware if you've got a plus or minus in it, it really messes things up. But if you don't have a plus or minus in it, we have kind of some cool things that start happening here. As we go to do a problem like this one, notice that we have x to the 6th divided by x to the 2nd. If we were to write out what this means, there's 6 x's on top and 2 x's on the bottom. We can cross out any like terms on the top and the bottom, and I'm left with 4 x's, so that would be x to the 4th. In number 16, the x squared is on top and the x to the 6th is on the bottom. When I do this, notice I still get those x's to drop out, and I'm left with x to the 4th, but they're in the denominator. So we still have to keep the x to the 4th in the denominator because they are on the bottom. So to maintain that, we'll just write 1 on the top. Remember, it's kind of like we divide the top by x, we divide by the top by x, so we're left with 1 on top and then those 4 x's on the bottom. With number 17, notice that we have 6 x's on top and we have 6 x's on the bottom. And every like term crosses itself out on the top and the bottom, and I'm left just with, if you want to think of it this way, 1 over 1. And we end up with just 1 as a solution. All the x's disappeared as we went through and did that. That should kind of make sense, because if you divide a number by itself, you always get 1, right? 7 divided by 7 is 1, 100 divided by 100 is 1, and so on. All right, so we can always just write things out like this in order to get ourselves some more information. Now let's kind of pull these over to the side a little bit and talk about some generalizations. If we have things like this, and as you start writing a bunch of these out, and again, if you ever get stuck, I always go back to writing them out. If you're confused about how the rule applies, if something's to the third power, write it out 3 times. And you can always recreate what these answers are going to be by doing them just like we did in these problems. But you are going to find that sometimes it's nice to be able to simplify things quickly. If you are multiplying 2 things or variables with the same base, so here's some general rules you can use if you like those. If we have something like x to a power being multiplied by x to a different power, so like here we had x times x to the second, what we can do is we can just add the powers together, x to the a plus b. That's kind of like this problem here. This was like x to the first and x to the second, and so I ended up with 1 plus 2. I ended up with 3 x's, so it was x to the third. So that's a way that we can do the rules. So we can always multiply big numbers, but when we're multiplying exponents, we add the powers together. Okay, oops. When we're doing, here's another example of a rule, and we did this a little bit up here when we had a group of things being taken to the third power. Anytime that you have one base of something and it's being taken to another power like this, we can just multiply those powers together. So, for example, x to the second to the third power would be x to the second times x to the second times x to the second, and that would be 6 x's altogether that way, 2 times 3. So here we were multiplying things with the same base. Here we have one base that's being taken to a power of a power, so that's the differences between those. Now, if you have different things that are being multiplied together, being taken to some power, we can just take each individual part. So x to the a power and then y to the a power. Anything that's outside, each thing inside can be taken to that power. That's kind of like what we did here with the 2x squared. We have to do the 2 squared to get the 4, and then we did the x squared to get the other part of the value. So that's another way that we can work with things. The last rule that we can follow is this. If we have x to the a over x to the b, we can subtract those exponents to get a new power. So, for example, here we had x to the 6th divided by x to the second, and what we're going to do is subtract the exponents, because the 2 on the bottom and this cancels out 2 of those on the top and leaves me with x to the 4th. So 6 minus 2 gives me x to the 4th for that solution there. So this rule for division is yet another one that we can do in terms of subtracting the powers. Now, something that I want you to pay attention to here, if you look here at number 16, we had x squared divided by x to the 6th. Well, notice if we subtract those powers, we end up with x to the negative 4th. Well, that's really interesting, because the answer that we got over here was 1 over x to the 4th. So what that really boils down to is the fact that if you have a negative exponent, it kind of means that we have a reciprocal of a fraction, that whatever that power is exists in the denominator. So it kind of flips its position a little bit. So it gives us some interesting negative exponent rules. Here, when we subtracted here we had x to the 6 divided by x to the 6. If we subtract those powers, 6 minus 6 gives me 0. And that gives us another interesting rule for us to talk about in terms of what does it mean to take something to the 0th power? Well, it means that everything got canceled out. There's no x's at all in my solution, and I just am left with 1. So we can use these rules, and again, use them as you're comfortable. You'll start to see these patterns emerge, and that's because they are, in fact, good patterns, and they work. But if you ever get stuck, don't be afraid to go back to writing all your 2x squareds out and counting your x's up, because that's always going to work, and it'll help you remind you of these rules and relationships as you work.